The last lesson in this unit is going to be on curve sketching, and essentially you've learned everything for this particular unit, and we're going to assume that we're sketching a curve without the use of a calculator. However, you are going to use your calculator to help you with the descriptions because you're going to be doing a lot of writing today. So let's go through the slides. So here's some guidelines for you to focus on and to remind yourself of. So the very first thing, move this up a little bit, you're going to have to determine what the domain and range of the function is. That's going to tell you where your undefined parts are and just help give you an idea of where vertical asymptotes are and horizontal asymptotes and that type of thing. Then you have to determine both the x and y intercepts. Most often x-intercepts, but then sometimes we also have to find the y-intercepts, and then any asymptotes, vertical and horizontal. So you have to review the rules for horizontal asymptotes. And then you're going to have to locate the values where the first and second derivative are either 0 or undefined. Because remember, with the first derivative, that tells us whether the graph is increasing or decreasing. And then the second derivative tells us whether it's concave, upward, or downward. And I will show you based upon these and remind you of how we determine whether there's a relative max or relative min, or if there's a point of inflection. Here we go. All right, so we've got 5 examples that we're going to run through, and they do take a bit of room. So write small. All right, and then for some things, for the graphing, I'm not going to show you all my work because my thought is at this point that you should know how to graph, although some of these are how to factor. Some of these are a little bit harder to factor, so oftentimes it's helpful to use your calculator to help you with some of those linear factors. For instance, so step 1, let me get some different colors up here. All right, so our first step here is going to be to find the intercepts. Whoops. Sometimes it's hard to write on this thing. Now I have graphed this graph here on our left for you. And that's the graph of this original function right here. So we're going to determine, now the assumption is that you haven't seen this graph and that you're going to use our knowledge to help you plot these relative max, relative mins, plot the intercepts here and here, and then determine whether the graph's going increasing, decreasing, that type of thing. But in this day and age, we full well know that we have use of a calculator, but we're going to use both at the same time. All right, so to find my intercepts, I need to look at the factored form. So we use the original graph to find the intercepts. So I'm going to start with setting f of x equal to 0 and putting this into factored form. So my original function, if I put into factored form, you don't know how to factor this. It's not one that you're comfortable with or familiar with. If I use grouping, it doesn't work. So I did go and look at my calculator and look at where it's crossing. So it's crossing the x-axis here at negative, it looks like it's crossing at -5 because this is going by 5s, 5, 10, 15, 20. So this is at -5. And then also this is about +1, and you can use the Calc menu on your TI calculator and look for zeros and use that feature to find those values. So because this is bouncing and this is an odd function, I know that there's going to be a double root here and a single root here. So I'm going to use that to help me factor this. So my factoring, I have one root at x equals -5, so its linear factor would be x plus 5. And because this polynomial has a degree of 3, I know I should have 3 roots. So then I must have 2 more roots, so that's why I know that at x minus 1, there should be 2 roots. So there's the factored form. Okay, so then based upon this, I can determine that the x-intercepts so for this one, the x-intercept is going to be at x equals -5, set that equal to 0, and at this x equals 1 if I set that equal to 0. So those are my x-intercepts. And then our second step is going to be, maybe I'll put my steps in green. Step 1, then step 2. All right, so for my second step, we are going to find the first derivative. So f prime of x is going to be 3x squared plus 6x minus 9. Then we need to find this, because remember from the first derivative we get our critical numbers, and those critical numbers are going to help tell us whether we have, we're going to use those to determine increasing and decreasing parts of our function. So the first thing I'm going to do is factor out a 3. So I get x squared plus 2x minus 3. And then the factors of 3 that subtract to give me 2. So you should know how to factor a quadratic. Would be x plus 3 and x minus 1. So there's your factored form. And so from this I can determine what my critical numbers are. So therefore, the critical numbers are so they are going to be, so from here we've got -3 and +1. So x equals -3 and x equals +1. All right, we have one more thing to find before we write out our findings. So then the next thing that we are going to look for is the second derivative. Alrighty, so f double prime of x equals. Now to find the second derivative, remember I'm just taking this and looping the exponent down. So I've got 6x plus 6. And then if I factor that, I'm going to factor a 6 out. So the factored form of that derivative is 6 times x plus 1. And so from there, we can determine our possible points of inflection. Remember, a point of inflection is where a graph is going from concave downward to concave upward. It's changing from going down to going up. So for this one, we're only going to have one. We're only going to have one. So therefore, the possible points of inflection set x plus 1 equals 0 would be x equals -1. So based upon this, I'm going to create intervals. So I need to create my x intervals. I'm going to take that whole x-axis from -infinity to +infinity and break it into parts. So how do I determine what parts to break it into? I'm going to use, I don't want my x-intercepts. I want my critical numbers. And then, so this one, and this one. So I've got the values of -3, 1, and -1. And so I want to put those in order from smallest to largest. So my smallest is -3, then comes -1, and then comes positive 1. So I'm going to go from negative infinity all the way to positive infinity. So we're going to create, for part 4, a table. And so this table is a little lengthy. And so I'm going to move it over here and give ourselves a little bit of room. And we want to put our intervals in our table. So I'm going to start with my intervals. So my first interval is going to go from negative infinity, and I'll create the table here in a minute. Let's put the intervals in first. So I'm going to go from negative infinity to that first number, negative 3. Then we have to also evaluate at negative 3, the end part of this interval, to see, is it a relative max or min, or is it a point of inflection? And so, or it could be undefined. And so then our next interval that we have to look at is going to be at x equals negative 3, just exactly at that value. And then we're going to go from negative 3 to our next number of negative 1. And then we have to stop at negative 1 and evaluate at x equals negative 1. Then we're going to go from negative 1 to the next number, which is 1. And again, we stop here at 1, and we're going to have to evaluate at x equals 1. And then finally, we go from 1 to infinity. Okay, so then this creates our chart, if you will. It's going to be a pretty long chart. We're going to have some small columns here. I'll tell you what to put in there in a minute. All right, right here is going to be our x intervals. So that's labeling that. Squeeze that in there. And then here is going to be the value of f of x. We're going to plug into the first derivative and plug into the second derivative. And then we're going to talk about the characteristics of the graph. Okay, and so I'm going to put rows here. So this essentially is you talking about all the characteristics of the graph. We've gathered the information, we just have to plug in the values. So remember, we've done this before. So you're going to take any value in between here and substitute it into the original function, the first derivative function, and the second derivative function. When we substitute into the original function, we are typically looking for an exact value if necessary. And we only actually do that at the x equals points. So the only time you're going to see me plugging into f of x is when it says x equals, x equals, x equals. So you might want to highlight those. So these are when we're going to plug into that. All of the intervals, so all of these intervals are going to get plugged into the first derivative function and the second derivative function. When we do that, we're just looking for a positive value or a negative value. So let's go ahead and get started. So for this first interval from negative infinity to negative 3, you might want to choose the value negative 4. So we're not plugging in here. We're not going to substitute into the original function. But if we substitute the value of negative 4 into the first derivative function, you will get a positive value. I'm not going to give you a number because you could substitute any value you wanted to. You don't have to substitute in negative 4. You could substitute in an infinite number of values so long as it's somewhere in this interval. But you can't choose your endpoints, right? You have to be in between. So whatever you choose in here, when you plug into the first derivative function, you should get a positive value. Then if you plug it into the second derivative function, you should get a negative value. We'll talk about how to identify the characteristics here in a minute. Then I'm going to actually substitute in negative 3, the actual value of negative 3, into all three of these. So if I substitute negative 3 into the original function, I get the value of 32. If I substitute negative 3 into the first derivative, I get a value of 0. And if I substitute into the second derivative, I get a value that is negative. And the reason why I'm giving you a negative and not its actual value, I'm going to always do that for the second derivative, because we use the second derivative to tell whether it's concave upward or downward. And I really prefer to look at it as a positive or a negative, because positive means it's concave upward, negative means it's concave downward. So it's just easier for me to look at. Okay, so then choose a value, some number between -3 and -1. I personally would choose -2. You can choose whatever you want to. That's the only integer that's in between there. So if I substitute into, I'm not going to substitute in the original function. So if I substitute into the first derivative, I'm going to get a negative value. And if I substitute into the second derivative, I also get a negative value. I'm not going to take the time on the video to actually do the substitutions and show you that. You can throw that into your calculator and do that later, but that's essentially what I'm doing. I'm taking -2 and plugging it into those two functions that we have above. And then the next one is x equals -1. If I substitute -1 into the original function, I get a value of 16. If I substitute -1 into the first derivative, I get a negative value. And if I substitute -1 into the second derivative, I don't get a positive or negative value. I actually get, whoops, that was terrible. I actually get 0. Now remember, 0 is neither positive or negative. So if the value in the second derivative is 0, you have to write it down as 0, because it will mean something in a minute. Here we go. Then somewhere in between -1 and 0, or somewhere between -1 and 1, you have to choose a value. Favorite value in there is 0. So I'm going to plug in 0. If I substitute 0 into the first derivative, I get a negative value. And into the second derivative, I get a positive value. Substitute 1 into the original function, I get 0. 1 into the first derivative, I also get 0. And so because it's neither positive nor negative, remember I had to put that 0. And then a positive number if I substitute it into the second derivative. And then finally, you can choose any value you want to in this interval. I'm going to substitute in 2. So subbing in 2 to the first derivative, I get a positive value. And subbing in 2 into the second derivative, I also get a positive value. So what does this all mean? So let's review a little bit from previously. The first derivative tells us whether we are increasing or decreasing as we go from left to right on the x-axis. So a plus means you're increasing, a minus means we're decreasing, and a 0 means that we're neither increasing or decreasing. So that tells me that I have a relative max or a relative min, because I'm neither increasing nor decreasing. I'm at nothing. So that typically should be a relative max or min. For your second derivative, that tells us whether we're concave upward or downward. So if I'm negative, that means I'm concave downward, which means it's going like this. If I'm positive, I'm concave upward, which means I'm going like this. And if I'm 0, that means it's a point of inflection, because I'm neither concave upward nor actually, it could be a point of inflection. You have to look to see what came here and what came there. So even though that 0 is a possible, this right here is a possible point of inflection. We'll talk about that as we look at the rest of the table. So let's go ahead and write down what we have. So for our first interval, because our first derivative is positive, we are increasing. So for space safe, I'm just going to abbreviate. So I am increasing. And because the second derivative is negative, I am concave downward. All right. At x equals -3, that value, when x is -3, y, because remember f of x is y, is 32, then there is no increasing or decreasing, so it should be a relative max or min. And if you think about it, I'm increasing, so I'm going up and up and up. And then down here, look at this one. My first derivative here is negative, so that means I'm decreasing. And then on top of that, the second derivative is negative, so I am concave downward. So if I were sketching that to go from anywhere from here to here, I would have to be increasing. I hit this point here at x equals -3 and I stop increasing. And then for this interval, I start going down. So I must have reached up and then down. I must have reached a relative max. And where did I reach the relative max? Right here at this point. So at the point -3, +32, because I went up and down, that's why I know I have a relative max. And you can see that above in the graph. Then, before we talk about what's here, because again, this is kind of different than what we had here. So at this x equals, we probably don't have a relative max or min because look here, I actually am decreasing here. So we have to look to see what's coming on either side of this interval, what's happening in this interval, and what's happening in this interval. So based upon our first and second derivative, the first derivative I am increasing, right? And the second derivative, I'm not concave up or concave down. So I went from, and then let's go down here and look at this one because I have to look at the one that follows it as soon as I have that 0. So I can kind of determine what's happening from this one through here down to here. So from here I must be decreasing. And then this says that I am concave upward. So let's think about what that looks like. So if I'm decreasing, both of these are decreasing, right? So, and then I'm at this point, -116. So if you look up on your graph, on your notes, and you look at the point, -116, and try to determine what's happening there, you'll see that we are decreasing, right? So starting from here to here, we're decreasing. And then, we're doing a concave down, so it must look like that, right? And then we have a concave up, still decreasing. Well, how is that possible? Well, let me show you down below that part of the graph. So we're going from a place, I'm going to sketch this and then probably erase it. So we're going from a place that looks like this. And the point that we're trying to determine what it is right here. That's that point, -116 on your graph. And as we're going to this point, now you see here, this right here is that relative max. Then we start coming down, that's the decrease. We hit this value here at -116 and we keep going down and into a relative minimum, as you can see down here. So although this is decreasing and decreasing, this is considered a point of inflection because this is concave down, this is concave up. Remember, your point of inflection is a switch from concave down to concave up. And as you can see, we have a switch here, concave down to concave up. In between these two, there has to be a point of inflection. If these two are the same, see how they're the same here and here, you're going to have a relative max or min. Because it's concave down, boop, boop, you had a relative max. Concave up, you're going to have a relative minimum here. So maybe I won't erase that, I'll leave that there. So then that means that we have a point of inflection here. Okay, so again, I knew I had a point of inflection. Number one, that was 0. And then you had to cause me to look above it and below it. Because these are opposites, this has to be a point of inflection. Here I had a 0, so that causes me to have to look above it and below it. See how these are the same? I have to have a relative max or min. The increasing to decreasing will tell me whether I have a max or a min. So then let's look here. I have a 0 and a plus. So at 1, 0, it looks like I'm going to have a relative max or min, or it could be a point of inflection, but we already know we only had 1. So I'm guessing it's relative min. And especially as I look at the graph, I know it is. But looking at my table, I also know that as well, because the 0 means that I'm not increasing or decreasing. And the plus means, I don't know, because of this. So it should be concave up. And let's see if that's true. It's going like this, so that looks right. So let's look down below it. For this particular interval, our first derivative is positive, so that means we're increasing. And then our second derivative is positive, so that means I am concave up. And based upon our previous discussion, these are the same. So if they're the same, I have a relative max or min. I went from a decrease to an increase. So I went decrease to increase. Right there, I must have a minimum. So that's how I know I have a relative minimum. So this is the one that we're going to spend the most time on, just me explaining how I determine this from the tables, and the rest of the table should go a lot quicker. So again, to recap, with relative max, mins, and point of inflection. I could have a relative max, min, or a point of inflection anytime I have an x equals. I only plug the x equals into the f of x in my graph. Every other part of my intervals, they all get plugged into the first and second derivatives, and I'm looking for pluses and minuses on those. Then I determine increasing or decreasing on concave up or down. So when I get to an x equals, I have to say, okay, what happened above it and what happened below it? If they're the same, like they are here and here and here and here, then these two right here have to be a relative max or min. That is determined based upon what's happening in the first derivative. We went from increasing to decreasing, so that's a relative max. Here we went from decreasing to increasing, so that's a relative min. I knew this was a point of inflection on this one here at -116 because above and below it, they're not the same, they're opposites. So that means it's a point of inflection right then and there. And notice that these are the same, these are opposite. So let's look at our next one. All right, so for example 2, I'm going to first of all make that a whole lot bigger. You can see the graph, and this is a degree of 4, so it's going to be harder for you to factor, put it into factored form. So our first step is to take the original function and try to put it into factored form if at all possible. So for this one, again, grouping doesn't work really well, so I graphed it. And if you look at the graph and use the Calc feature menu and find your zeros, you will find, and I know based upon the fact that the degree is 4, I should have 4 zeros. So as you can see on this particular graph here, I'm going to make it a little bit bigger, then I'll put it back down. So you can see on this graph here that it crosses the x-axis here at 0, and if you use your Calc menu and find the 0, it will tell you that this value is 4. This crosses and this crosses. So it's going to be hard for you to determine whether, does this have 3 roots and this has 1, or does this have 3 roots and this has 1? How do you know? Well, number one, I know that I'm going to go ahead and shrink this back down. If I look at the original, keep shrinking. And a smidge bit more, there we go. I know that if I look at the original function, I can factor an x out of every single term. So for step 1, I'm going to take f of x and I'm going to factor it. I know I can factor out an x, and I get x to the third minus 12x squared plus 48x and minus 64. So based upon that right there, there is only one value for x that is 0. The rest of this must factor, because remember this is to the 4th, so I have 3 more zeros left. The rest of this must factor, and you can keep dividing it. You can do long division, right? Or synthetic division. I would prefer synthetic division. So I would use synthetic division and keep dividing this by 4, because we used our calculator to look for that. And if I divide this by 4, I can keep dividing my result over and over again by 4 3 more times until I'm left with a constant. And so that's how I knew that this factors as x times x minus 4, and I was able to divide it using synthetic division 3 different times. So I know that I have 3 x minus 4s that divide into that. If you forget how to do synthetic division, you need to watch a YouTube video. It's real quick. It should be like a 5-minute video. It'll refresh your memory. All right, so that's our factored form. Based upon that factored form, I know that I have x-intercepts and also looking at the graph. So therefore, the x-intercept are x equals 0 and x equals 4. So those are things that I want to plot on my graph. Now they're not going to go into my table of values at the very last step. But those are things if I were sketching this graph, because remember that's what this section is over, is curve sketching. I would definitely want to cross the x-axis at 0 and 4. All right, so then step 2, we're going to find the first derivative. So f prime of x is equal to, I'm using the original one, 4x to the third minus 36x squared plus 96x minus 64. Well, we have to factor that one too. So in order to factor that one, because it's a cubic, I tried grouping. That didn't work. So then I went to my calculator and I just graphed this to look to see where it might intersect the x-axis. And it intersected the x-axis at 1 and 4. Well, I have to figure out, well, first of all, I do know that 4 divides out. 4 is the greatest common factor, so I'm going to factor that out. So we have to factor that out. So I get x squared, or x cubed, minus 9x squared, plus 24x, and then minus 16. Then I proceeded to use this right here, and I used synthetic division, and because I had already graphed this in my calculator, and I noticed that in the calculator, this graph here crossed the x-axis at 1 and at 4. So I used synthetic division, and I divided 1 into here, and found out that 1 only divides in once. And I took the result after I divided it by 1, and I divided that result by 4, and I got another x minus 4. So I know that there are 2 x minus 4s and 1 x minus 1. So, whoops, so it factors as x minus 1, x minus 4 squared. So I am expecting you to do some of this on your own as far as that synthetic division. So based upon these numbers here, your first derivative gives you your critical values. Those critical values could be where there are relative max and mins. So set each one of these equal to 0. And at this point, it doesn't matter that there's 2 x minus 4s. So therefore, the critical numbers are x equals 1 and x equals 4. Now these are 2 values that we're going to use for our x intervals in our tables. We're not going to use the x-intercepts. We use only what we get from the first and second derivative. So then third step, I need to find the second derivative. So when I find the second derivative, I'm using this one up here. Makes it easier. And so for the second derivative, I get 12x squared minus 72x plus 96. Now you ought to be able to factor quadratic. So the first thing I want to do is factor out the greatest common factor. So 12, 72, and 96 all have a 12 in common. So I'm going to factor that out to make life easier. And then, what factors of 8 add to give you 6? Well, that's 4 and 2. And the signs are going to be x minus 4 and x minus 2. And so remember, the second derivative gives us our possible points of inflection. So therefore, f double prime of x is equal to 0 when x equals 4 and x equals 2. And so you could put there in parentheses possible points of inflection. So at this point, we've gathered everything that we need to do that whole big table. We're going to gather all of our information. So you need some room. So if you might do this on the back of your notes, I write really big, so I had to really squeeze it in. All right, so I'm going to put the numbers, oh, and then these are our other numbers that we need as well. So this time we have 4 numbers. So I'm going to put those 4 numbers in order. So actually, let me move this back up. So my 4 numbers are 1, I've got 2 4s and a 2. So 1, 2 4s, and a 2. So if I put those in order from smallest to largest, I have 1, whoops, that didn't write. I have 1, 2, and 4. So I'm going to go from negative infinity to 1 to 2 to 4 to positive infinity. All right, so at each of these values right here, those are also going to be x equals. So my intervals are going to be from negative infinity to 1, and then we have to do x equals 1, then from 1 to 2, and then we have to do x equals 2, from 2 to 4, and then we have to do x equals 4, and then from 4 to infinity. So those are the intervals I'm going to place in my table. So I'm going to start to set up my table. Okay, so those are all my intervals. So these are my x intervals. Okay, and this is going to be f of x, f prime of x, f double prime of x. And then this is going to be my characteristics. And I'm going to squeeze in graph. Okay, then I want my rows. Whoops. All right. So now, remember, the only ones that I'm going to substitute in to f of x would be x equals 1, x equals 2, and x equals 4. Otherwise, those are the only 3 that we're going to plug into the original f function. All right? Everything else gets substituted into the first and second derivative. Here we go. So between negative infinity and positive 1, I am going to choose 0. So if I substitute in 0 into the first derivative, I got a negative, and into the second derivative, a positive. I'm not even doing my characteristics right now. I'm just filling in f of x, f prime of x, and f double prime of x. And then at x equals 1, if I substitute 1 into the original function, I get negative 27. And then into the first derivative, I get 0. And then into the second derivative, remember the second derivative, I always want just pluses or minuses or 0. Same thing with the first derivative. I would just want pluses, minuses, or 0. I don't actually want a value. So I did have to put the 0 for that first derivative. For the second derivative, if I substitute in 1, I get a positive. Then from the interval from 1 to 2, I'm going to have to choose 1.5. So I'm going to substitute 1.5 into the first derivative, and that gives me a positive value. 1.5 into the second derivative gives me another positive value. Then we're going to substitute in 2 into the original function and all the derivatives. So 2 subbed into the original function is negative 16. 2 subbed into the first derivative is positive, and subbed into the second derivative is a value of 0. Then in the interval from 2 to 4, I'm going to choose 3. So if I substitute 3 into the first derivative, I get a positive value. And the second derivative, I get a negative value. At x equals 4, I'm going to substitute 4 into all 3. So when I substitute 4 into the original function, I get 0. Into the first derivative, I get 0. And into the second derivative, I get 0. So we'll talk about that. And then in the last interval, I'm going to substitute in 5 in between here. So only in these two. So substituting into the first derivative, I get a positive value. And in the second derivative, a positive value. So for everything that is not in equals, I'm going to determine whether it's concave up or down and whether it's increasing or decreasing. So the first derivative tells me whether it's increasing or decreasing. So I'm just going to go here. So I'm just going to go straight down. So just on my first derivative. So I've got decreasing for this one. Skip the x equals. Then I have increasing for this one. And for the next interval, we are increasing. I guess I should put a little semicolon there. And then increasing. So I totally skipped the x equals ones. We'll come back to those because they're either relative max, relative min, or points of inflection. And then I'm going to use the second derivative to determine whether it's concave up or down. So this one is concave up because it's positive. This one is concave up because it's positive. This one is concave down, downward, because it is negative. And this is concave up because it's positive. So remember what I said about these two. If these two are the same, you're going to have a relative max or min. So think about what these two are doing. We're going decreasing, so decreasing, and then into an increase. So it's a dip, it's a valley, so we must have a minimum because it's at the bottom. So this right here is a relative minimum at 1, negative 27. And then looking at this one, these are not the same. And so it must be a point of inflection as soon as these are not the same. And notice that these are the same. They always will be for a point of inflection. And so point of inflection. And you can look at the graph up there and see. Remember, a point of inflection means that we're going from a concave up, meaning looking like this, to a concave down, meaning looking like this. Oops, like this. Sorry. So we're going from an up to a down. So somewhere it's breaking that. And the point of inflection is not a relative max or a min. So bear that in mind as well. All right, then here you're going from concave down to concave up. So they are different as well. So that should also be a point of inflection. Again, notice that these are the same. So we're going to go back and look at that graph here in a minute. So this one has 2 points of inflection. Okay, so let's go back and look up at the graph above. Oh, where'd it go? Okay, I'm going to make that bigger so it's a little easier to see. Okay, so on this graph, from negative infinity, and I know I had to really squeeze that in there for you to see all the parts, but from negative infinity to positive infinity, from negative infinity to positive 1, so from here till we get to here, the graph is decreasing, right? And it's concave upward because it's going down like this. It's opening up. Then we have a relative min all the way down here at 1, negative 27. And then from 1 to 2, we are increasing, and that's a concave upward because it's opening up. And then we reach this point at 2, negative, or what is it, 2, negative 16. So right here at 2, negative 16, somewhere around here, the graph changes from concave upward to going concave downward. See how it's got this little blip right here? That's your concave downward. And then this little point right here, which is neither relative max or min, it's changing from a concave downward to this concave upward. So that's why it becomes another point of inflection. You see this little part of the S curve. So that one's kind of a weird one. It has 2 points of inflection, one right after another. So let's look at the next graph. All right, so graph 3, we now start to get into some more complicated. You can hear my Vishla getting very anxious in her crate. I had to crate her so she wouldn't bother me while I'm taping. So this one requires a little bit more effort in factoring. You got to factor the numerator separate from the denominator. And then you have to look at the factors. If this x minus 2 can cancel the factor up here, remember it's a removable discontinuity, so it becomes a whole. If it doesn't cancel out, it becomes a vertical asymptote. So that's a little bit of a summary there. And then also, we could have horizontal asymptotes as soon as we have a quotient. So remember, you're looking at the degree of the numerator versus the degree of the denominator. So here's a real quick synopsis of that, a little review. If the degree of the numerator is smaller than the degree of the denominator, your horizontal asymptote is y equals 0. So if the degree of the numerator is greater than the degree of the denominator, as you see here, degree is 2 versus the degree of 1, then there is no horizontal asymptote. And then finally, if the degree of the numerator is exactly equal to the degree of the denominator, then you set the leading coefficients as a ratio. And so if these were both 2 and 2, then you would have 1 over 1, so it would be y equals 1. So remember, you take the ratio of the leading coefficients if they're equal. They're not here on this one. So what do? Here we go. Let's start off with step 1. So this one's a little bit different because I want to talk about some vertical asymptotes and some y-intercepts and some x-intercepts. So I'm not going to do like step 1, step 2, step 3. I am, but there's a few extra steps on this one because it's a little bit more complicated of a graph. So the graph is undefined. And I'm just going to put undefined at x equals 2. Now, whether that's a whole or an asymptote, you don't quite know yet. So in order to determine that, you might want to try to factor it. Well, ask yourself, are there any factors of 4 that add to give you 2? No. It's not factorable. You're going to have to use a quadratic formula in order to determine what values or what the factors are of x, what would let x be 0. So we're going to talk about that in a minute. So that means that this is not going to divide out. So in this particular case, I know that x equals 2 is a vertical asymptote. So you might want to put that there in parentheses. I ran out of room, but you probably have room on your paper. All right, so then the second thing that we want to look at is the y-intercept. So the y-intercept is 0, negative 2. How did I get that? Well, remember on the y-axis, every x value is 0. So all I had to do was substitute 0 into the original function. That makes this go away, this go away. So the value of the numerator is 4. That goes away. The value of the denominator is negative 2. So 4 divided by negative 2 is negative 2. So that's how I got the y-intercept. And you can see right here, there's the y-intercept at 0, negative 2. So that's an important thing that you need to plot. Then the third thing that we're going to look at is setting the numerator equal to 0. In order to find the x-intercepts, the only thing, if you'll recall, that will create this fraction to be 0 is if the numerator is 0. So I have to take this and set it equal to 0. Well, we already determined it's not factorable. So you have to use a quadratic formula. So I'm not going to write all this out. I do in my notes that I put online. But if you set the numerator equal to 0 and solve for x, you'll find that you have to use that quadratic formula. And if you do use the quadratic formula, the opposite of b plus or minus the square root of b squared minus 4ac all over 2a, you will find that you do not have any real roots. And as you can see here on the graph doesn't even cross the x-axis. So use the quad formula to determine that there are no x-intercepts. Now you might want to write there in parentheses that you only use the numerator, because that's the only part of that fraction that's going to create that fraction to be 0. 0 can't be in a denominator, but 0 can be in the numerator. All right, so we know we have no x-intercepts. So then the fourth thing we need to look at are horizontal asymptotes, because we have a quotient. So we already talked about this, because the degree of the numerator is greater than the degree of the denominator. So since and I'm going to abbreviate this, of the numerator is greater than, you can put a greater than symbol if you want to, the degree of the denominator there are no horizontal asymptotes. So that's the fourth thing with a quotient that you have to look at. Okay, next thing is our derivative. So I'm going to go ahead and find the derivatives and give you the value for the derivatives quickly, because they take a lot of room and a lot of time. We've already gone through how to find first and second derivatives of these kinds. So if you need to review that information from when we were in school before the quarantine, go ahead and look at those notes. But I'm just going to go ahead and find your first and second derivatives quickly. So here we go. First derivative is equal to x minus 2. Oh, I might not have room on here. I might have to move it over. Let's do that. It'll just make life easier. All right, so x minus 2 times, times 2x minus 2 minus x squared minus 2x plus 4, and then it was times 1. So there's no, that's the derivative of the denominator is 1, so I didn't write that in there. All over the denominator squared. Okay, then you have to simplify this. If you simplify this, you should get, and factor, because we want to factor. So to do this, you're going to want to multiply this out, distribute this negative, combine like terms, and then refactor. If you do that, you will find, quite simply, that you have x times x minus 4 all divided by x minus 2 squared. Now, as I'm looking at your homework, when you do the homework on this section, if you skip your steps in finding your first and second derivative, I'll know that you're just copying off the homework, and I will dock you for not showing enough work. So I'm purposely skipping these to save time on the video. All right. Then step 6, I'm going to move over here because I'm going to need some room for this one, is the second derivative, which requires quite a bit more room. Actually, maybe I'll move that over even more. There we go. All right, so 6. All right, so f double prime. All right, so I am going to use, when I find the second derivative of this one, if I were you, I would look at this one right here, but with this distributed, like x squared minus 4x. That's what I would use for your numerator. So just to let you know that that's where I'm getting my numbers from. Okay, so I'm going to end up with x minus 2 squared times 2x minus 4 minus x squared minus 4x times 2 times x minus 2, all divided by x, your denominator squared is going to be x minus 2 squared squared, which is x to the 4th. Then you're going to have to distribute and multiply out. So if I were you, I would factor out. So this one and this one have an x minus 2 in common. So I would actually factor that out so that you're left with an x minus 2 times a 2x minus 4 minus this times this. Then you'll multiply those together, collect like terms. And when you do that, you end up with x minus 2, because that's what we're going to factor out from the very beginning. And then what's left multiplies out to give you this. And I would just suggest that you try it on your own and see if you can come up with these values. If you can't, then ask me questions regarding, well, how did you go from there to there? And I'll write it out the long way for you. And then x minus 2 to the 4th. So then from here, you can start to do some simplifying. So the 2x squared and the minus 2x squared are going to cancel. And the negative 8x and the positive 8x are going to cancel. And then on top of that, this x minus 2 can cancel with one of the x minus 2's downstairs. So you end up with a final answer of 8 over x minus 2 to the 3rd power. And so that is our second derivative. Whew. Now, when you look at the second derivative, because remember the second derivative is how we get our points of inflection. So since there's no way for the numerator to have a value of 0, the second derivative has no zeros. And since x minus 2, if you set that equal to 0, you get x equals 2. X equals 2 is not in our domain. So the graph has no points of inflection. So you're not going to see any on this particular case. So I would write that down if I were you. So let's go ahead and write those little comments. Remember, that's because the numerator cannot possibly be 0. So we are not going to get any points from the second derivative to use for our intervals. I don't know why I couldn't think right there. Let me see if this is going to let me move it now. Oh, I knew it. Well. See that little F double prime is moving with me? Ignore that. All right, so then over here, I'm going to write out, I'm going to see if I can get rid of this. Oop, that didn't allow it. Let's see if I can get it. Oh, it's letting me get rid of it. Fab. Okay, so now, what is this, step 7? So this is step 7. Here is our table of values. So in this step, we need to look at our values. So from step 5, our critical numbers are 0 and 4. Now, I'm going to add other numbers in here other than 0 and 4 because I also know that we have a vertical asymptote at x equals 2. So that's a break in our domain. So any breaks in the domain are part of our interval. So we've got the numbers 0, 2, and 4. So that's how I'm going to create my intervals. So I'm going to start from negative infinity. My smallest number that we just talked about is 0. I'm going to go to 0. And then we have to stop and evaluate x at 0. And then we're going to go from 0 to 2. So 2 is my next number. We're going to stop and evaluate x at 2. Then we're going to go from 2 to 4. We're going to stop and evaluate x at 4. And then finally go from 4 to positive infinity. Okay. And so these are my x intervals. And this is f of x, f prime of x, and f double prime of x. And these I'm going to abbreviate characteristics of graph. Okay. And then my rows. I do expect to see this table of values as part of your work on your homework. If you don't have that, you're going to lose points because it's part of you showing your work. Okay, remember, we are only substituting in to f of x when x is 0, x is 2, and x is 4. Other than that, we're ignoring it. So let's go ahead and substitute in those values. So at x equals 0, if I substitute that into the original function, I get negative 2. Into the derivative, I get 0. And into the second derivative, I get a negative. And if I substitute x equals 2 into the original function, I get undefined, into the derivative undefined, and into the second derivative undefined. So that right there, and we already determined this, is our vertical asymptote. Right? And then at x equals 4, if you sub that into your original function, you get 6. Sub it into the first derivative, I get 0. And in the second derivative, I get a positive value. All right, so then the rest of these I'm subbing into the first and second derivative. So for the first interval, from negative infinity to 0, I am going to choose to substitute in negative 1. If I substitute negative 1 in, I get a positive number in the first derivative and a negative in the second. The next interval of 0 to 2, I'm going to choose 1. So if I substitute 1 in to the first derivative, I get a negative, and the second derivative, I get a negative. And in the interval 2 to 4, I'm going to substitute in 3. And so into the first derivative, I get a negative value, and into the second, I get a positive value. And finally, our last interval of 4, I'm going to substitute in 5. So into the first derivative, I get a positive, and the second derivative, I get a positive. So based upon my first derivative, which tells me whether it's increasing or decreasing, I get the following. So I get increasing. Here I get decreasing. Here I get decreasing. And here I get increasing. Remember, at all of our x equals, we're skipping those because they're either points of inflection, max or mins, or in our case here, a vertical asymptote. All right, so then our last thing we need to look at is the second derivative, which tells us concave up or down. So a negative tells us it is concave down. So a negative here, concave down. And a positive here, concave up. And then here, concave up. All right, so we have left to figure out what these points are at 4, 6, and at 0, negative 2. Now you can look at your graph as well, but remember that if we're going concave down, if they're the same, I should have a relative max or min. Up and up, relative max or min. So you want to look at the increasing versus decreasing. So here I'm going from increasing to decreasing. So I'm increasing, then decreasing. That's a max. So this right here, excuse me, is a relative max. Okay, then this one here, I'm going from decreasing to increasing. So I'm decreasing to increasing. So that's going to be a relative minimum. All right, next graph. So this one is somewhat similar to the last one that we did. I'm gonna make it a little bit bigger. There we go. And it's an odd graph, and you can see on the graph I took all of this and I used brackets here and parentheses here when I put it into the y equals. And you end up with two vertical asymptotes, which you can see right here, which we're going to talk about that. And it's almost factored for you. We have to factor this binomial and this binomial. They're both the difference of two squares. So moving all this over, let's go ahead and get started. So let's start by factoring the original function. So f of x is equal to 2 times x plus 3, x minus 3, x plus 2, x minus 2. Now nothing cancels out, so there are no holes. This gives us a couple of things. So I can figure out my vertical asymptotes. So vertical asymptotes from here. So I'm just going to start writing down a bunch of stuff. So let's start with those vertical asymptotes. So my vertical asymptotes would be at x equals 2 and x equals negative 2. And so I got that from my denominator. Then from my numerator, I can get my x-intercepts. So set the numerator equal to 0, set this and this equal to 0. So I get x-intercepts at negative 3, 0 and at 3, 0. And then a y-intercept, I'm going to move over here a little bit, y-intercept. Now remember, on your y-intercept, the x value is 0. So if I substitute 0, it'd probably be easier to substitute it into the original function. If I substitute 0 in here, I get 2 times negative 9, which is negative 18. Substitute 0 in here, I get negative 4. So negative 18 over negative 4 is a positive 9 halves. So that's how I got my y-intercept. And horizontal asymptotes, let's talk about that. Horizontal asymptotes, because it's a quotient. So the degree of the numerator here is 2. The degree of the denominator here is 2, based upon those leading coefficients. So if you were to distribute the 2 all the way through, the leading coefficient to this x squared term would be 2, and the leading coefficient to this x squared term is 1. So remember, when the degrees are the same, to find the horizontal asymptotes, you take the ratio of their leading terms coefficients, so 2 over 1. So I know that my horizontal asymptote is going to be y equals 1. 1, 2. Where did I get 1 from? No idea. Let's try 2. All right, so 2 over 1 is 2. All right, so we've collected all of that, and all of that is stuff that you've had before. So the next is to find our first and second derivatives so that we can get our critical numbers. I'm having an issue with the number 1. Wow, it's late. It is currently 11:30. Nothing like waiting until the last minute. Don't I tell you all not to do that? I was enjoying my spring break. Okay, so again, I'm going to remind you, I'm going to skip some steps. So to find the first derivative, I am going to take the constant of 2. I'm just going to multiply it through. So I'm going to find I'm going to use x squared minus 9 as my f of x, and my x squared minus 4 as my g of x, if you will. And so I end up with x squared minus 4 times 2x minus x squared minus 9 times 2x. Oops. Let's move that back. Get rid of that. Okay. starting all over x squared minus 4, and then that is squared. And then if you go and simplify it, multiply these together, distribute the negative, multiply by 2, you end up with the following. You get 20x all over x squared minus 4 squared. So based upon this, we only care about what is going to make the first derivative 0. So I don't care about the denominator, I care about the numerator. If you set the numerator equal to 0, then that means that x is 0. So therefore, the critical number is my handwriting seems especially difficult and terrible today, sorry. So the critical number is, I'm using a different stylus, that could have something to do with it, is x equals 0. So that's one of the values that I'm going to use to find my intervals in my chart. Okay, now step 3 is going to be our second derivative. All right, so for this one, I'm going to need a lot more room. So let's move this over. Here we go. That should give me enough. Okay. So I'm going to take, and I've got x squared minus 4 squared times 20, and then minus 20x times 2 times 2x times x squared minus 4. I told you I need some room. All over x squared minus 4 squared, which as we did before is to the 4th. So then you're going to simplify what you can. So if I were you, I would factor out the 20 from both of these, because this is one term, this is another term. So I'm going to factor the 20 out of both of them. So I'm only going to square this and multiply the 2 to the x to the 2x and then to this and simplify everything. And then refactor. So if you do that, oh, and actually if you think about it, you can take out a 20 and you can take out an x squared minus 4. Oh, that might make it a lot easier. So if you factor out a 20 and an x squared minus 4. Like for instance, this one you're going to have an x squared minus 4 left, and over here you're going to have an x, a 2, and a 2x left. And so then if you combine those, you end up with times x squared minus 4 minus 4x squared all over x squared minus 4 to the 4th. All right, so then I can cancel this x squared minus 4 with one of those, and I can combine these two terms in here, and I'll factor out a negative while I'm at it because you don't have to, but I don't know. It's nicer to have your highest degree term positive. So that's what I choose to do. So then, whoops, I'm change it to blue. So we equal negative 20 times 3x squared plus 4 all over x squared minus 4 to the 3rd. So let's evaluate this to see if there are any points of inflection. So this is the only place that could cause the numerator to be 0. Whether x is positive or negative, when squared, it will become positive. There is no way that you can take a positive number and add a positive number and get 0. So there is no possibility for there to be a 0 for the second derivative. So since has no zeros, so this is just like the last one we did, talk about the denominator. And x equals, if you factor that denominator, you'd have x plus 2x minus 2, right? So x equals positive and negative 2 are not in the domain. You can conclude I'm going to move that up so that I don't have a problem like I had on the last page. So there are no points of inflection. Okay. Now, I want to do a table of values. Oh, where am I going to put that? Here we go. So I'll just put it all down here. So step 4, table of values. So for our numbers for our interval, ow, I just hit my knee on my desk. That really felt terrible. I'm sure it was pretty loud. Sorry. Whoops. All right, so the only numbers that I have, remember I have to take into account breaks in the domain. So the numbers that I have to work with would be -2 and +2, because those are our breaks in our domain. And then from step 2, we had a critical number of 0. And so that's it. So I've got -2, 0, and 2, +∞, -∞. So I have to break up my x-axis into those intervals. So here we go. So -∞ to -2, and then remember we have to stop and evaluate at -2, and then we're going to go from -2 to 0, stop at 0 and evaluate at 0, then we're going to go from 0 to 2, stop and evaluate at 2, and finally from 2 to infinity. So these are our x intervals. This is f of x, f prime of x, and f double prime of x. And these are characteristics of the graph. Okay, so remember that at our x equals, that's the only place that we evaluate for f of x. So here, here, and here. So let's go ahead and do those. So if I substitute in -2 into the original function, I am going to get undefined. And let's just look at the first and second derivative while we're at it, because it is undefined in all three of those. And then at x equals 0, we've already substituted that in because that was our y-intercepts. And then into the first derivative is 0, and into the second derivative we'll get a positive value. And then for x equals 2, that is undefined on all three because that's part of the denominator. All right, so now we're going to finish out the other intervals. So in the first interval, from -∞ to -2, I am going to substitute in -3 into the first and second derivative. And if I do that, I get a negative on both of those. In the interval from -2 to 0, I will substitute in -1, and I get a negative value in the first derivative, and a positive in the second. And in our next interval from 0 to 2, I'm going to substitute in 1, which is fairly simple to sub in. I'll get a positive on both the first and second derivative. And then our last interval, from 2 to infinity, I choose to sub in +3. And in the first derivative, I get a positive, and in the second, a negative. So I'm going to start off by filling in my information for the first derivative, which is increasing or decreasing. Remember, at all the x equals, I'm going to halt and not determine whether it's increasing or decreasing there. All right, so for the first interval, I get decreasing. Then the next interval, decreasing. Next is increasing. And then increasing. And then our second derivative tells us whether we're concave up or down. So for the first interval here, I am concave downward. Next interval, concave upward. Next interval, concave upward. Next interval, concave downward. Okay, so then we have to make determinations as to what these are. Well, the two undefined we've already determined are our vertical asymptotes and then we just have one left. So for this one, you want to look above it and below it. So remember, if these are the same, then you must have a relative max or min. So go and look at whether it's increasing or decreasing. So we go from decreasing to increasing. So decreasing to increasing makes a valley, so it means we have a minimum. So this is a relative minimum. And that's it. Last problem. Here we go. All right, this one's fun because of the fractional exponents, but don't let that bother you. It's really not that bad. If you put this into your calculator, you get an interesting graph where you have this kind of thing going on here. So here we go. Now, first step, we want to look at factoring the original function. So how do you factor something with a fractional exponent? They both have a denominator of 3, which is handy. And so 4/3 is smaller than 5/3. So I can actually factor out an x to the 4/3 from here and an x to the 4/3 from here, because I can just subtract it out. That's the same thing. Remember, when dividing, when we pull out a greatest common factor, we're dividing by that. And when we divide like bases, we subtract the exponents. So to factor out this original function, I'm going to take out the GCF of x to the 4/5 or 4/3. They don't have any coefficient in common. So then 2 divided by 1 is still a 2. And then x to the 5/3 divided by x to the 4/3. When dividing like bases, you subtract the exponents. So 5 minus 4 is 1/3. So x to the 1/3. And then minus -5 divided by 1 is your -5. And then x to the 4/3 divided by x to the 4/3, it cancels out. So here we go. So that's our original factored form. From there, I can find my x-intercepts. So this one's really easy because any monomial is always 0. So my x-intercepts are going to be x equals 0. And then for the other one, you're going to find out that it is x equals 125 over 8. How did I get that? So here we go. So down here, let's see, to figure out this one, I'm going to just put a little star here. And over here, I'm going to show you how I did that. So I took this right here. Remember, we're setting it equal to 0. So I'm going to take that, 2x to the 1/3 minus 5, and set it equal to 0. So I'm going to solve for x. So I'm going to add 5, divide by 2, and then I want to raise this to the third power, because if I raise 1/3 power to power, remember we multiply, so 1/3 times 3 is going to make 1, and I want to make this x to the first. So what I do to one side, I must also do to the other. And so I get an x on the left, 5 to the third is 125, and 2 to the third is 8. So that's how I got my 125 over 8. That was fun. So then step 2, now we're going to have to find the derivative. So don't let the fractions bother you. Remember, you're not going to use this, you're going to use this one to find your derivative. So take 5/3 and multiply it by 2, then subtract 3/3. Take 4/3, multiply it to -5, then subtract 3/3, because you're subtracting 1 from those exponents. You're always bringing it down by 1. So I got my first derivative by doing what I just told you, and that would be 10/3 x to the 2/3 minus 20/3 x to the 1/3. Then we want to write that in factored form. So if you look at their coefficients, I can factor out the numerators have a 10 in common and the denominators have a 3 in common. So I can factor out a 10/3 out in front from each of those coefficients. And then out of these two, this is the smaller one. So x to the 1/3, and I can factor that out of here and x to the 1/3. So I'll be subtracting, right? So I'm going to put an x to the 1/3 out in front, and then each of these will get divided by 10/3 x to the 1/3. So 10/3 divided by 10/3 is 1. 2/3 divided by 1/3, x, you're going to subtract those exponents, so you get x to the 1/3. So x to the 1/3. Then if you think about it, this divided by this, I'm basically going to be left with a -2, right? And then these are going to cancel out completely. So I get just a -2. Then to determine my critical numbers, because the first derivative gives me my critical numbers, I'm going to set each of these equal to 0. So this one is a monomial, so it gives me 0. And this one, I'm going to do the same thing, set this equal to 0. So I would add 2, right? So I get x to the 1/3 equals 2, and then raise this to the third power, raise that to the third power. So I'm going to get x equals 8, right? So if I let 8 be x, 8 to the 1/3 is 2, minus 2 is 0. So therefore, the critical numbers are x equals 0 and x equals 8. You can look at the notes that I put online. I went through that x equals 8, how I got that on there. We're not going to do it on here again because I literally just did that number 1. You can do that the same yourself for part 2. All right, so then step 3 is to find our second derivative. So again, same thing. I'm going to take this one right here, multiply 2/3 to here, subtract 3/3. Multiply 1/3 to here, subtract 3/3. If you do that, you end up with something really fun. I'm being facetious. So you get x to the negative 1/3 this time, and then minus 29ths x to the negative 2/3. So out of our variables here, x to the negative 2/3 is actually smaller, so I can factor that from each one of these. And they both have a 29ths in common. So the factored form here would be 29ths. I'm going to factor out an x to the negative 2/3. And I would be left with x to the 1/3 minus 1. In order to see our vertical asymptotes and restrictions to domains, we really need to write this in its proper fraction form. So the 20 is going to go in the numerator of our fraction, the 9 is going to go in the denominator, so I'm going to split that into a proper fraction. So the 20 will go here, and the 9 will go here. Then because this is negative, it's going to go into the denominator. So I get x to the positive 2/3. And because this is positive, it's raised to the 1 power. It's going to stay in the numerator. So it's x to the 1/3 minus 1. That's it. Now, some possible points of inflection. So remember, points of inflection are caused by the numerator here becoming 0. So this isn't going to cause any 0 here. But if I set this equal to 0, I'm going to add 1 and then raise both sides to the 3rd power. So x is going to be 1. I also have to look at any undefined values. So because if x were 0, it would cause the denominator to be undefined. Remember, that's one of the things in that very first slide that I showed you that could cause a point of inflection. So although it doesn't create a 0, it creates an undefined value. So therefore, possible points of inflection. We won't know till we look at our table. And it's hard to look at the graph and determine it as well. All right, so we have 1 at x equals 1 and x equals 0. So these are values that are going to cause breaks in our intervals. So I've got 3 different numbers actually. I have 0 twice, and then 1 and 8. So I'm going to put those in order from smallest to largest, and we're going to set up our table and our intervals. So our first interval is going to go from negative infinity. Our smallest number out of steps 2 and 3 is going to be 0. And we have to stop and evaluate x at 0. And then we're going to go from 0 to our next smaller number, which is 1. Then we have to stop and evaluate x at 1. And then we're going to go from 1 to our next number, which is 8. We have to stop and evaluate x at 8. And then finally we can go from 8 to positive infinity. And we are almost done. Okay, and so this one is x intervals. Okay, so remember we are going to substitute in to the original function only these 3 values here. So if I sub those in, I get for x equals 0, I get 0 for the original function, 0 for the first derivative, and undefined for the second derivative. So we'll come back to that. And then for x equals 1, I get negative 3 for the original function, a negative value for the first derivative, and 0 for the second derivative. And then for x equals 8, I get negative 16 in the original function, 0 in the first derivative, and a positive value into the second derivative. So then let's look at all the intervals. So from negative infinity to 0, I'm going to plug in negative 1. I get a positive value for the first derivative and a negative for the second. Between 0 and 1, I'm going to have to substitute in 1/2. And so I get negative and negative. And between 1 and 8, I'll probably substitute in 2. And if I do that, I get negative and positive. And then in the last interval from 8 to infinity, I'll substitute in 9. And I get a positive and a positive. So based upon the first derivative, I would have increasing on this interval, decreasing on this one, decreasing on this interval, and increasing on this one. And then for the second derivative, that's my concave up and down, I would have concave down for this interval, concave down for this interval, concave up for this one, and concave up for this one. So then to determine what these three blanks are, you want to look at what comes above and below it. So these two are the same. So remember, when they're the same, we have a relative max or min. So look to see what's happening here. We're going from increasing to decreasing. So we're increasing to decreasing. That creates this hill where we'd have a relative max. So I have a relative max at the point 0, 0. And then the next one, these are different. So as soon as they're different, I know I have a point of inflection. And notice that these are the same. So this is a point of inflection. It's where the graph is changing from concave down to concave up. And then for this last blank part here, notice that these are the same. So that means I have a relative max or min. Look at what's happening here. I am decreasing and going to increasing. That's a valley, meaning I have a relative minimum. And you can go back and look at the original graph that we put there, and these are accurate and true. All right, so now for the last slide, you don't really have to write anything, it's real quick. So here we go, I'm gonna make this much larger. These are just some sample polynomial graphs, just to remind you of a couple of things as you go through and do your homework following this. Here we go. All right, so remember, anything that has a degree of 0, which is a constant number like y equals 5, is going to be the graph of a horizontal line. A linear function has a degree of 1, so it's either going to be tilted negatively or positively. And whatever the coefficient of x is, if it's negative, you'll have a negative slope. Positive, you have a positive slope. That's in y equals mx plus b form. And then quadratic functions have a degree of 2, and they are your parabolas. So they are opening up or down, and you can tell that based upon the coefficient of the highest degree term. So if the highest degree term is positive, as you see here, it will open up. So it will be going decreasing to increasing, or it'll be concave up, right? And then, so that would be a relative minimum. And here this would be a relative maximum, because you'd be going from increasing to decreasing. And you can see that the coefficient of the square term is negative. And then these are all examples of cubic curves. So if the coefficient of your leading term, your x cubed term, is negative, you're going to see, and you learned about this in Algebra 2, that your left and right hand behavior determine that. So if it's negative, your right hand would immediately go down, and your left hand would have to go the opposite of it, because it's an odd function. So in an odd function, the left and right hand behavior are opposite of each other. So notice that when your leading coefficient on your x cubed term is positive, your right hand side is going up towards positive numbers, and your left hand side is going down. So that's just a summary. Please text me with questions on things that you don't understand or things that I went through too quickly on this video. So good luck, and let me know what you think.